Today we'll take a look at how to create a bolt universal connection from a selection recipe. We'll begin by creating a splice plate assembly. I'm going to create two plates 8 by 8 by 1/10 of an inch. Then I'll create a component from one of the plates, and then I'll duplicate that component to create my assembly. So here we'll have a 4-inch overlap, one plate on top of another. Now that we've created the plate component, we'll go ahead and assign a material to the body. Here we'll put 4340 on the plate, and then we can create our component finite element model. I'm going to create an idealized part because I'm going to create a mid-surface, and then we'll create a shell mesh. So here to mid-surface, in the idealized part, first I'll promote, then mid-surface. Then we can edit bodies to use because I had selected none originally because I knew I wanted to bring in just the mid-surface. And then we'll mesh that at 1/10 of an inch. Now a few things to note: we're inheriting by default the material onto the mesh, and we're also inheriting the thickness. And we can confirm that that was mapped correctly by plotting the thickness contours. Here you can see that 1/10 of an inch thickness. Now that we've created our component finite element model, we can create our assembly finite element model. We'll go ahead and unpack the components, select both of them, and say automatically map to associated finite element models. And we get both of those plates brought into our assembly finite element model. Next we need to model some bolts. If we don't already have some bolts modeled, in this case we don't, and we're an analyst and we want to try and determine how we want to position those bolts, we'll go ahead and create a new finite element model off of our assembly that we'll call bolt, and we'll allow curves and lines only into our fem. We'll go to the eye part, and this is where we'll define our bolts, and we'll define them just with lines, and these lines will be on the axis of the bolt. So I'll make a 2-point line between these 2 points to define my first fastener. Now, before I create more, what I'll do is assign an attribute, and this will be used later in defining our selection recipe. So I'm going to create a name on that curve, making sure that I select the curve and not the curve feature in the selection bar. And then we can go ahead and pattern that curve. And here I've specified an XC and YC direction, count, and pitch distance for each in order to define 4 fasteners. Now, because I defined a name on that curve before I patterned it, here if we select the properties of one of the pattern curves, you can see it has that bolt name on it as well. Alright, so here you can see our fem just has the curves in it. And next we'll go to our A-fem and add that bolt definition fem to it. And there you can see the curves now are in our A-fem. Now we can create a selection recipe off of those attributes on those curves. We'll select strategy as attribute, give it a name bolt, input filter will be entire model and curve, and then we'll select a name attribute of bolt, and I hit the tab key and you'll see that it will select all of the items that have that attribute assigned to it. Next we can create our bolt universal connection, and we'll walk through the dialog top to bottom on the left. There's no selection for general for this one. For targets, we'll make sure we select the flange polygon bodies that we want to bolt together. Then for our bolt axis definition, we'll select set of curves, and this is where we're going to select a selection recipe, which is that bolt selection recipe we created earlier. We'll select add axis, and you can see it gets all 4 locations. Next we'll define the physicals for our shank diameter, head, and nut diameter. We'll use the location endpoints as limits for our maximum connection length, and then we'll specify a material for our fastener. Here I'll choose 310. And you can see it creates a representation of the fasteners, but they're not yet realized. To realize them, we need to select what type of elements we want to use to realize the bolt connection. So here I'll select C-beam and RBE2. Now if you get an information message saying that some shank elements are not long enough, so they've not been created, and you can decrease the minimum shank element length value to avoid this, the way you get that is by going into connection elements and selecting the minimum shank element length here and making it smaller than the distance between your plates. And here I have 1/10 of an inch. So I'll specify a minimum shank length that's less than that. Alright, so now you'll see that our bolt connection is up to date. And if we'd like, we can take a closer look at each of the individual 1D elements that were created to model the bolt. Here, to see that a little bit better, I'll turn off the bolt universal connection. Here you can see the spiders for the nut and the bolt, and there you can see our shank element as our C-beam. Alright, let's go ahead and resolve any label conflicts in our assembly FEM, and then we can create a new sim. And here I'll create a linear static solution, making sure that we have output requests selected for grid point force. Here you can see I've got that selected. You can preview all of our output requests here. That looks good. Next we'll put in a load and a constraint. I'll go ahead and deactivate my subcase so that my loads and constraints will be global. Here I'm selecting an edge to assign a fixed constraint and an edge to define a unit load, putting our splice plate in tension by putting the vector in the Y direction. Alright, we're ready to solve. This run takes just a few seconds, and we're ready to view our results. Alright, so we're really interested in the forces on the fasteners, so I'll select the grid point forces in the Y direction. And to see those forces a little bit better, I'll go ahead and turn off our RBE2s and our shell elements. And here you can see, if I double click mouse button 1, it will fit the view. And it's a little bit easier to see as an arrow plot, so I'll turn on arrows instead. And as a double check, we can identify results on one end of our beams, on all of them, and see that they sum to the 1 pound that we applied. So there you can see our individual loads on our individual fasteners. Now, if we want to make a change, let's say that that load is too great and we need to add more fasteners to distribute the load. Let's go back to our pattern, and we can change the count and pitch distance in order to increase the number of fasteners connecting our splice plate. So you can see those curves have updated in our bolt FEM. We can go to our AFEM and go ahead and update the AFEM. And what you'll note is the bolt connection says that 4 out of the 8 have failed. And this is because our customer default is set for that minimum shank element length a little bit too small, and it gets it from the customer default. So we need to reassign it for those other 4 as well by making a small change to that length. We'll take a look later at how we can edit our customer defaults if you're going to be making splice plates that have a small distance between them, so that you don't have to go through making those changes each time. So here, to see the difference between our original solution, I'll go ahead and clone our original solution and solve. And then we can view our results top and bottom for our grid point forces. Then we'll go ahead and turn off our RBEs and shells and make an arrow plot and synchronize the views. So there you can see the individual fastener loads have reduced by increasing the number of fasteners. Now, to make that change to customer defaults, what we'll do is go to File, Utilities, Customer Defaults, Simulation, Pre-Post, Universal Connections, Bolt. And then we can decrease the minimum shank element length.